All right, part two of introduction to water treatment. All right, disinfection. Disinfection involves the destruction and inactivation of organism which may have objection with the standpoint of the health aesthetics. In so much as the health of the water they consume with the principal concern of these responsible for supplying with the water design facility of disinfection must necessarily be carefully executed. Chlorination application for the chlorine water preferred method for disinfecting water supplies. Definitions. The terms frequently used with the connection with chlorination practices are defined as follows. Chlorine demand. The difference between the chlorine concentration of chlorine added with the water, the concentration of chlorine remaining then specified with the contact period. Chlorine demands vary with the concentration of chlorine applied at the time of the contact temperature and water quality. Chlorine residual. Total concentration of chlorine remaining in the water at the end of the specified contact period. Combined available residual chlorine, any chlorine in which we have the combined nitrogen. Most common source of the nitrogen is ammonia. Compounds form a reaction between chlorine and ammonia is known as chloramines. Chloramines, the disinfecting power of the combined available chlorine is about 25 to 100%, 100 times less than that of free available chlorine. Free available residual chlorine, the part of the chlorine residual which has not been combined with the nitrogen chlorinated practices. Alright, combined residual chlorination, combined result chlorination entail the application of sufficient quantity of the chlorine ammonia, and ammonia is not present in raw water to produce the desired amount of the combined available chlorine, chloramine, and the water. The efficient enough ammonia is present with the raw water to form combined chlorine residual. Only chlorine needed to add water combined residual chlorination is generally used only when maintaining adequate free chlorine residual in the distribution system is difficult with injectional high level. The total trihalomethanes would be formed as a result of the free residual chlorination due to consideration of the other total trihalomethane control alternatives should be made using chloramines. Water containing ammonia, certain nitrogenous organic matter reacts with chlorine. In addition, with chlorine causes the formation of the chloramines until the ratio of less than element chlorine to ammonia compound is about 5 to 1. For the addition of the chlorine, result of the oxidation chloramines to gaseous nitrogen oxides. Increase the quantity of the chloramines present after all chloramines have been oxidized. Additional chlorine added to the water formed the free available chlorine. The points available the chlorines have been oxidized. Only free chlorines formed in pre-breaking point. If no ammonia is present with the water, there will be no breaking point. The chlorine required to reach the breaking point is usually 10% of the ammonia nitrogen content of the water. However, the shrimp waters because of the presence of the chlorine consuming substances such as 25 times the ammonia nitrogen concentration may be required. Enough chlorine should be added past the breaking point to ensure adequate free chlorine residual. Marginal chlorination. Marginal chlorination involves the application of chlorine to produce desired level of total chlorine residual, regardless of the relative concentrations of free combined chlorine are present in marginal chlorination, and for the initial chlorine demand has been satisfied by some oxidizable substance remain. Alright, your chlorine dosages. Figure 2-4 provided the minimum cystolytical bacterial free chlorine residual. Minimum bacterial combined chlorine residual varies in pH temperature levels. Since waterborne bacteria are a major concern of fixed installations, minimum bacteriolide levels maintain a treatment water in all parts of the distribution system under constant circulation. Even lower pH level, the free chlorine residual should not fall between 0.2 milligrams a liter. Combined chlorine residual should not fall below 2.0 milligrams a liter. Marginal chlorination is practiced for the total chlorine residual must not be less than 2 milligrams a liter. Whenever epidemiological evidence indicates the outbreak of non-bacterial wasteborne decrease in MPS, infectious hepatitis, schistosomiasis in an area of fixed military installations, cystolytical free chlorine residual should be maintained in the water supply. And then it shows a chart of the minimum chlorine residuals. Other effects of chlorination. In addition to the disinfection achieved with the chlorination, beneficial effects should be noted since oxidizing power chlorine is high and present with 3 chlorine, hydrogen sulfide is oxidized nitrates and are oxidized to nitrates, soluble iron, magnesium are oxidized in soluble oxides. Free chlorine also reacts naturally, occurring taste and odor coloring, producing organic substance, chloro-organic compounds, trihalomethanes. U.S. EPA, after much discuss over cost benefit, the cost of maximum contaminant levels served above 10,000 persons, has indicated a water treatment industry to avoid cost modification of existing plants to reach U.S. EPA future maximum contaminant of the total trihalomethane. Most significant change of the disinfection practices will be required. Application of chlorine. Chlorine may be applied to water in 2 forms as gaseous element chlorine or trihypochlorite salts. Or gaseous element chlorine should be used with the water disinfection as all fixed installation. Cost of hypochlorite salts is prohibited in all plants larger than 0.5 mg a day. For remote site fixed installation, some of the well sources require 5 gallons per minute or less. The source will be small. Demands can use hypochlorite disinfection. Alright, the point of application. Chlorine may be applied to water, various locations, water treatment plant, storage facility, distribution system. Absolutely essential for the chlorine applied with the water quickly through the mixed with the water undergoing treatment required with a special chlorine mixing facility should be provided. Conventional water treatment plants. Chlorine may be applied prior to any other treatment process, pre-chlorination, following one or more of the unit treatment process, post-chlorination, and again more distant points of the distribution system, dechlorination. Pre-chlorination has often been used. The water would be maintained chlorine residual entire treatment period. The length of the contact time, the colligation, flocculation, filterization process were thought to be improved by pre-chlorination of the water. Nuisances, algae growth, and settling basins were reduced pre-chlorination of the chlorines, usually injected with the raw water at near raw water intake. Pre-chlorination must be accepted the practice for the disinfection in the past. However, since many surface waters contain tetrahalomethane precursors that will combine with free chlorine during pre-chlorination form potentially carcinogenic trihalomethane such as chloroform, point of application has been shifted further down the treatment process to take advantage of the precursor removal during treatment. Okay, post-chlorination. Post-chlorination generally involves the application of chlorine immediately after filterization. Hi, Mama. Alright. Alright. Cool. Immediately after filterization, a handful of clear water designed with a construction water treatment plan should include the necessary provisions for changing location. Chlorine application that may be desirable for improving the treatment of the disinfection process. Dechlorination is the practice of adding chlorine to water in distribution system. Maintain minimum chlorine residual throughout the system. Chlorine equipment and hypochlorite salts must be applied with the water in solution form. The hypochlorite solution pumped with the diaphragm pump through an injection system of the water to be chlorinated. Its elemental chlorine is used with the disinfection should be injected with the solution type chlorinator. Since chlorine solutions are acidic, main components of the chlorination system must be constructed with a corrosion and resistant materials such as glass, silver, rubber, plastic. Maintain the chlorination apparatus trouble-free state with essential key spare parts, repair kits for chlorine system must be kept on hand. Critical components of the chlorination system shall be installed in duplicated automatic control. Automatic chlorination control is utilized with the chlorine feed rate should be controlled by primarily with the rate of flow of water with a signal from downstream residual chlorinized analyzer used to trim the feed rate. Provision of the manual control during an emergency situation must be included. Superchlorinated dechlorination. Superchlorination may be necessary for the large variation of chlorine demand. Variable the contact time is brief. Water that which have superchlorinated generally requires dechlorination before discharge to the distribution system. Dechlorination may be achieved through application of sulfur dioxide, sodium bisulfite, sodium sulfite, or bypassing water with granular activated carbon filters. Dechlorination process. Subsequent dechlorination, if necessary, is controlled with the free residual chlorine remaining in the water is less than 0.2 milligrams a liter. Careful monitoring must be practiced to ensure that the potential harmful level of total trihalomethanes are not exceeded. Safety precautions of chlorination. AWWA Manual Safety Practices. Water Utilities contain safety recommendation regarding use of chlorine. Alternate disinfection. Use of the chlorine disinfection causes the unacceptable loss of concentration chlorinated with the organic compounds. If all other methods of reducing total trihalomethanes have been exhausted, such as moving the point of the chlorine aeration, special colorant chlorine form, which mainly constitutes the total trihalomethanes. In many cases, the alternate raw water source, such as groundwater source, is not available. As alternative disinfection must be considered. The alternative disinfection includes install primary means of water disinfection scales and should have the disinchlorination facilities available to above operate standby use. 5. Alternative disinfection discussed below. Ozone, chlorine dioxide, chloramines, ultraviolet radiation, UV, and ozone combined. While chlorine is at least coefficient deficient, the desired dosage and energy consumption basis. However, the alternate disinfection are not significantly more expensive. Alright, ozone is extremely powerful disinfection. It has been used in Europe either with a sole disinfectant in conjunction with a post-chlorination in part persistent chlorine residual water distribution system. In the United States, potable water plants have post-use of the ozone. The cost, control, taste, and odor today. Ozonation is being increasingly used in primary disinfection prior to rapid mixing, flocculation, and filtration. Accidental ozonation does not produce trihalomethanes. It reduces the oxygen, does not leave any residual disinfection. Hence, the need for post-chlorination. Ozone is generally electrical and either the use of the electrical discharge gap corona technique, air and oxygen stream, cooling water stream, and alternating electrical current are required. Efficient cooling is essential to reduce the thermal decomposition of the ozone bowl. The diffuser period of the most economic ozone controller available. Alright, chlorine dioxide is a highly effective disinfectant with the produce of minimal trihalomethanes present with the precursor of the chlorine dioxide. The United States have been limited with the taste and odor control, has been used elsewhere with the primary disinfectant present, receiving more attention for the United States. Common method of the chlorine dioxide production of the recent chlorine gas from a conventional chlorinator with sodium chloride solution for the mixing of the chlorine and sodium chloride streams prior to the introduction of the mainstream of the mixed stream in the past for the column contractor to maximize the chlorine dioxide production, max disadvantage of chlorine dioxide formation of chlorate and potential toxic. Alright, chloramine. Due to the chloramine, the disinfectant fell into the disuse after the introduction breaking point chlorination to achieve the same disinfection ability of the chlorine. 10 to 15 times the amount of the chlorines are needed. Longer contact time is required. More chlorines are needed with a high concentration. Organic materials are found with the influent water. Chloramines are easy to generate and feed and produce a resistant residual that will remain through the water distribution system. Chloramines may be produced with introducing ammonia to the water stream prior to the addition of the free chlorine process optimized for the minimum trihalomethanes production and minimize disinfection. However, there has been concern over the chloramine toxicity. Ultraviolet radiation have undergone a development and not been used for large scale with drinking water disinfection. Most of the uses include the product process water disinfection, where high purity sterile water is needed. The UV radiation has been used for disinfection draining drinking water remotely located hotels, cruise ships. For large scale water processing plant, UV disinfection, although application is feasible, UV disinfection does not leave the disinfection residual and should be accompanied with the post-chlorination. Ultraviolet irradiation is also effective in oxidizing organic compounds in water. Water turbidity will affect the effectiveness of UV disinfection. Alright, UV and ozone recently have been experimental and is combined with UV and ozone contactors. Result of the test shows premise there is no water treatment plant operating with this method of disinfection. Alright, fluoride adjustment, health effects. Excessive fluoride concentration damages the teeth of the children. Water for the period. On the other hand, moderate concentration, 0.7 to 1.2 milligram a liter, are beneficial to general children's teeth. Most natural water contain less of the optimum concentration of fluorine. Upward adjustment of the fluorine concentration can be achieved with the application measured amount of the fluorine chemical to water. Fluoridation chemicals most frequent used in the fluoridation are sodium silicofluoride, sodium fluoride, and fluorosilicic acid. Particular installation choice of chemicals depend principally on the delivered cost and availability. Sodium fluoride, the chemical, is commercially available with a white crystalline powder having a purity of 95 to 98%, sometimes artificially called Nile blue. Volatility is approximately 4% at 770 degrees Fahrenheit. The pH of saturated solution is 6.6. 100% of the pure material contains 45 by 0.25% fluoride. It is also available in 100-pound bags or 125 to 400-pound drums in bulk. Sodium silicate fluoride. The compound is commercially available with a white powder purity of 98 to 99%, volatile only about 0.76% at 770 degrees Fahrenheit. pH of saturated solution of 3.5%. Material contains 60.7% fluoride and is available in 100-pound bags, 125 and 400-pound drums in bulk. Alright, flow-silic acid, chemical commercially available liquid containing 25 to 30% of the weight of the flow-silic acid. It's dissolved with 13 gallons of carboys, 55 gallon drums in bulk. 100% pure acid contains 79.2% fluoride. pH on 1% solution 1.2. Use the flow-silic acid fluoridation agent in water. Low alkalinity will significantly reduce the pH of the water. It should not be used. The fluoride adjusts the waters of the type of the unit unless the pH adjustment is also provided. Alright, your point of application. Since for the water path with the point of ejection with the fluoridation chemical with the flow rate pass with the point known with a reasonable accuracy of the water treatment plan preferred application point, usually with the combined effluent of the air filter fluoride chemical can be added with an earlier stage of the treatment. For example, the combined filter and effluent, but part of the fluoride will apply with the removal of the filterization product. The coagulant lime softening will also remove the small amount of the applied fluoride. A large dose required with the offset with the treatment process of the loss of the groundwater and supply source of the fluoride chemical should be injected with the discharge pipe of the well pump, where some apply in several wells, each pumping independent of the distribution system will be necessary to provide injection point. Each well, the flow of the pass of the injection point is variable. The automatic equipment will feed fluoride chemical at a rate proportional to the flow's requirement. Alright, fluoride feeders. Volumetric gravimetric dry feeders equipped with the dissolvers suitable for sodium fluoride, sodium silicate fluoride. Feeders should be equipped with weighing the device accurately measuring the weight of the chemical feed each day with the feed of equipment should be designed to minimize the possibility of free flow flooding chemical through the feeder. Normally, the feed machine supplied with the hopper should not be more than 100-200 pounds of chemicals. Large distance with the hopper holding the general quantity of the dry fluoride chemical increases the danger of flooding. Overfeeding are not recommended with the most installation. Solutions of the sodium silicate fluoride or acidic corrosion or resistant dissolvers in solution piping must be provided with the chemical is employed. Flow-silic acid is used and can be applied by means of small metering pump with open channel and a pressure pipe storage of the tank feeders of the piping. The flow-silic must be for the corrosion resistant material. The acidic, slightly volatile and feed system should be enclosed. If not enclosed, special exhaust ventilation should be provided to protect personnel from fluoride fumes. Fluoride removal. Fluoride removal can be accomplished by the passage of water through the beds activated with alumina, bone char, and tricalcium phosphate. Capacity bed film to remove the fluoride is exhausted. It can be regenerated with the treatment caustic soda solution, followed by rinsing acid neutralization with a residual caustic soda. Other methods of fluoride removal into the electrodialysis, reverse osmosis, ion exchange. Some fluoride reduction can be obtained watering softened using excessive lime treatment. The fluoride reduction method associated with the magnesium precipitation. Some fluoride removal is a function of the amount of the magnesium precipitated in water. Our removal process procedure limited waste for the suitable provisions must be made at all of their disposal. Guidance as to the fluoride removal process can be employed, obtained with a laboratory study of the process. Fluency fluoride removal capacity uses samples of water that is to be treated. Alright, taste and odor control. Most taste and odor surface waters are caused by low concentration organic substance derived with decomposing vegetation, microscopic organisms, sewage, industrial waste, pollution, etc. Treatment for taste and odor removal involve the destruction of the odor substance by chemical oxidation, removal of the aeration, absorption of activated carbon. Chemical oxidation agent which have an effect with which can be used with the treatment of potable water with chlorine, chlorine dioxide, potassium permanganate, and ozone. No single chemical is completely effective under all operating conditions. Aeration is helpful in eliminating odor caused by the hydrogen sulfide, but is ineffective with significantly reducing odor associated with the dissolved organics. Absorption. Powdered activated carbon, commonly used with the removal of the taste and odor, color by absorption. Colors applied with water at any point with the treatment plant prior to the filterization, but usually advisable to apply earlier in the treatment process with the prolonged contact for maximum effectiveness. Carbon should be applied well ahead of the chlorine, preferably in advance with lime softening influent with a pre-sedimentation basin. Normally effective with the carbon applicant point. Powdered carbon doses usually range from 5 to 10 milligrams a liter, but as much as 50 milligrams a liter may be required. Use the powder activated carbon adds in suspended solids to increase the amount of sludge, thereby creating a sludge disposal problem. Powder activated carbon may have marginal effect of reducing the total trihalomethanes. Granular activated carbon is as so has been treated with the taste and odor removal is employed as a separate treatment step, forming carbon columns and substitute for sand in filterization process. Used in this way with granular carbon serve the dual capacity of the filterization medium. The taste or odor removal of the granular activated carbon is also excellent at reducing total trihalomethanes. Granular activated carbon must be reactivated with a regular basis with the kept with the absorptibility to remove the cost of the reactivation of the granular activated carbon. Other methods of taste odor control reduction total trihalomethane should be considered. Aeration generally most cost effective other than granular activated carbon contractors. Alright, 210 softening. Whether water softening is provided depending entirely on the type of the project. Either made with the water or the two general type of the process used are softening of the lime soda ash process and cation ion exchange or volylate process. Iron and magnesium control. Occurrence of iron and magnesium. Dissolved iron and magnesium are encountered primarily with the groundwater devoid with dissolved oxygen. Normal oxygen-jaded surface water do not contain significant concentration of these metals. However, stagnant water found at the bottom of the thermally stratified reservoir sometimes contains dissolved iron and magnesium. The presence of the solution is associated with the anaerobic condition at the near and bottom of the reservoir. Effects on iron and magnesium. Dissolved iron excess of 1 to 2 milligrams liter will cause unpleasant taste staining with the water to develop a cloudy appearance. Iron concentrations appreciably greater than 0.3 milligrams will cause red stains in plumbing fixtures and laundry. Similar magnesium will cause black stains if in the presence of extent more than about 500 milligrams deposit of iron magnesium can build up water distribution system. Periodic flush outs of these deposits result in injectional order of turbidity and consumer tap. Alright, removal of oxidizing and filterization. Oxidization can be accomplished by the dissolved oxygen by adding aeration, adding the addition of the oxidizing chemicals such as chlorine, chloride, dioxide, potassium permanganate, or ozone. Maximum manganese is more difficult than iron to oxidize and precipitate. The absence of the manganese, iron can often be removed in minimum treatment consisting aeration, followed by the direction filterization. General aeration will not oxidize manganese unless the pH is raised to about 9.5. Stronger oxidants such as chlorine, potassium permanganate are effective with a lower pH value to ensure the oxidation, precipitation, and agglomeration of iron, manganese, and their essential complete removal. At least three treatment steps are usually necessary: aeration, contact time, filterization, aerator containing trays of coke, limestone, etc. Commonly used reaction time is provided by a contact sediment basin having a detention period of at least 30 minutes. Filterization accomplished with a conventional signal multimeter filter design. Filterization rate at least 3.3 gallons per minute per square foot. Aeration steps frequently supplemented by chemical oxidation, chemical chlorine, permanganate fluctuation advantages in the contact basin, particularly with iron exceeds 2 milligrams a liter. Or removal of the ion exchange is the cationic exchange, sodium zeolite softening process under the proper condition capable of removing the limited amount of dissolved unoxidized iron and magnesium. For application of the process, it is essential that the raw water, wash water, contain no dissolved oxygen. The sum of the iron and magnesium concentrate not exceed 0.5 milligram pressure of the oxygen. High concentration of iron and magnesium will cause rapid fouling of the exchange of resin, subsequent cause for the removal capacity following curved treatment of the resin. Sodium bisulfite solution diluted hydrochloric and sulfuric acid will be required to restore capacity. Removal of lime soda ash softening. Lime soda softening is effective as means of removing both iron and manganese. Stabilization iron and manganese. Under some circumstances, stabilization iron and manganese will be application of the polysulfide compound may be acceptable. Iron and manganese in the water are maintained with a dispersed state, but through the completion action polysulfite compound dosages about 5 milligrams per liter of the sodium hexamethiophosphate for each milligram of liter for each magnesium are responsible effective. However, the total phosphate dosage should not exceed 10 milligrams a liter. The phosphate polyphosphate stabilizing compound must be added to water prior to chlorination. If the chlorine is applied first, the oxidizing iron magnesium to insoluble forms, rendering the stabilization agent effective stabilization with a concentration of iron magnesium excess approximately 1 milligram a liter, but generally not satisfactory. Also, stabilization does not persist if the water is heated above. The heating converts the polyphosphate, but the orophosphates would have no stabilizing power. Stabilization also helpful, not suitable for the iron and magnesium removal. Magnesium removal in general should be viewed as temporary expedient to be used in pending installation with removal facilities. Art 212, or corrosion scale control. Corrosion can be defined with the deterioration of metal to direct chemical with electrochemical reaction in the environment. Scale referral to the accumulation of solid precipitated out of the water. Water treatment with the corrosion and scale are closely associated, but they are conserved in the connection with the design operation of the treatment work. The scale may be desirable because it can provide a measure of protection against the corrosion. However, the thick layers of scale are detrimental both for the hot and cold water. So it's essential to produce the balanced water near highly corrosive in order to acceptably scale forming. Hard corrosion. The extent of the nature of the corrosion reaction depends on the many factors. One of the most important, the chemical physical nature of the water, the velocity of the pipe, the metallurgical of the pipe, the coating, existing system, when the corrosion of the problem. Most of these factors, the exemption of the chemical nature of the water, not readily susceptible to change. The consequence of these situations, the emphasize of the most place adjustment of the water's chemical quality as only practicable the means of the corrosion control. Existing system controllable factors are principal the calcium content, alkalinity, and pH. Certain corrosion inhibitors can be used, but those refused are suitable for the bottled water system. Treatment to ensure the deposition and maintenance of the thin layer of calcium carbide with a pipe of the interior of the one widely used the maintenance of the corrosion control. This control method, will not infallible, has been fairly successful in minimizing the corrosion rate of the iron pipe. The rate of the formation of the calcium carbonate is favored by high concentration calcium bicarbonate, carbonated alkalinity. Protection of this type of the type cannot be attained when waters containing very low concentration of calcium alkalinity. Corrosion rates may also be reduced by even certain inhibitors of the potable water system. Practical inhibitors, silicates, and certain polyphosphate compounds. Sodium silicate can be used to a limited extent with very soft water. Polyphosphates can be applied to the scale as well with the corrosion control. They are considered most effective with the corrosion control, but the pH range of 5 to 8, and their effectiveness is greatly influenced by velocity. Low velocity, such encountered with the dead end mains, reduce effectiveness of all corrosion control methods. Dissolve the oxygen, carbon dioxide have significant effect with the corrosion rates. Carbon dioxide lowers pH, makes the water more aggressive. The carbon dioxide can remove chemically, but is generally not feasible to attempt chemical remove. Oxygen with a potable water supply, most sufficient surface waters are normally saturated with the oxygen, while groundwaters, essentially free of oxygen, usually absorb some of the during treatment with the distribution when consideration removal of the carbon dioxide. Aeration should be kept in mind. While the efficient aeration will remove most of the carbon dioxide, it will, in doing this, practically saturate the water with the oxygen. Corrosion rates influence some of the extent of the mineral substance of the ground water. The corrosion effect with the interrelated, but not possible to isolate with the quantitative influence of the individual ions. It is known high concentration chloride sulfide ions will produce the increased corrosion rate. However, the adverse effects of the somewhat mitigated alkalinity, carbonate, bicarbonate, calcium ions to obtain appreciable benefit of alkalinity. Calcium total alkalinity expressed as calcium carbonate should not exceed 50 milligrams a liter, probably range from 5 to 100 milligrams a liter. Calcium concentrate calculated with the calcium carbonate should also be at less than 50 milligrams a liter. General high concentration alkalinity and calcium, the greater water capacity of the corrosion retardation. On the other hand, excessive calcium alkalinity often result in subjectional scale formation. It is therefore necessary to seek the compromisable between corrosion on one hand and scale formation on the other. are based on the corrosion acceleration effect of the chloride and sulfite with the corrosion inhibiting effect of the alkalinity. The following ration term corrosion index has been developed with a pH range of 7 to 8 and the presence of dissolved oxygen index below with a 0.1 indicate probable general freedom from corrosion index higher than 0.1 indicate with a corrosion tendency with a higher index with the greater the probability of the corrosion. Are 212 scale problems distribution are caused principally by calcium carbonate, magnesium hydroxide, aluminum hydroxide oxides, and hydroxide magnesium and iron. Aluminum hydroxide deposits can result with excessive aluminum use of the coagulation, improper coagulation practices such as poor mixing and flocculization, incorrect coagulation pH of aluminum hydroxide can create soft white deposit having the rippled surface with the produced reduction in pipe carrying capacity measured. Halazins will see value. The problem is one after the other. Precipitation aluminum hydroxide. Aluminum remains in solution only until after filtration. Chlorination, which often flows in filtration, reduces pH slightly. The chemical nature of the aluminum is such that a slight reduction in pH will result in significant reduction in solubility. Alright, magnesium. Magnesium hydroxide deposit that causes serious difficulty distribution system hot water heaters. Magnesium vulnerable in high sensitivity of the pH temperature. Failure to exercise careful to control overstabilization following softening usually led to the deposition problem. The absence of the detailed information regarding scaling tendency of given water and advisable to maintain magnesium hardness between 40 milligrams a liter to pH below 9.8. Hot water heaters should be operated so that the water temperatures will not exceed 140 degrees Fahrenheit. Alright, your iron and manganese hydroxide deposits, hydrous oxide deposits, the iron and manganese are an inevitable distribution system handling water contaminant more than about 0.3 milligrams a liter for the oxide, 0.05 milligrams of magnesium. Severity of the problem is directly related with the concentration of iron and manganese. The best solution is to remove them at the source. Less satisfactory producers attempt to prevent their precipitation. Polyphosphate treatment as the source. Iron deposits may also be caused by corrosion reaction with a lost scale of the tubular curls. Severe cases cleaning and lining of the pipe may be required. Tubular curl formation can be minimized through corrosion control. And then it goes into an exam for the introduction of water treatment program. Was the introduction to water treatment.